Hi, ladies and gentlemen. Welcome to week 8 of distance learning. I am Mrs. Rubalcaba. You all should know that by now. So something a little bit different for this week instead of my usual PowerPoint presentations. So for the assignment, I hope you guys finished watching those 2 videos and also answering those questions. And you should have reached the last part of the assignment, which is my part. Also, the reminders, as always, is to make sure that you take your attendance every day, once every day. And also my flex hours, Monday and Tuesdays, Mondays periods 1, 3, 5, and Tuesdays reserved for periods 4 and 6. All right, so on to chemical equilibrium. Let me see. Oh, it's not attached. Okay, excuse me. So onto chemical equilibrium, there's that equation that you guys should have learned by now. Okay. So we've got our usual chemical equations, but this is the general one that is expressed. So one of the reactants represented by A's, the lowercase a is the coefficient. There that. And possibly another reactant reacting there should be expressed like this also, and it's a double arrow. Okay, so equilibrium, remember that there is a forward and a backwards reaction, and will be expressed by the products, also lowercase and capital letters there. Okay, and your chemical equilibrium equation should be represented as this, where we've got the concentrations of the products over the concentration of the reactants. Okay. And the chemical equilibrium tells you if the reaction is going to move towards the forward reaction, as in there's going to be more products than there are reactants. But if it's going the other way, then the constant should be smaller, and that indicates that there will be a lot more reactants than there are products. But remember that we have chemical equilibrium when the rate, as in the speed of the reaction going forward, is the same as the speed of the reaction going backwards. It doesn't necessarily mean which parts, it doesn't mean that both sides will have equal amounts, reactants and products. It doesn't mean that. It just means that they have equal speeds of going backwards and forwards. That's what chemical equilibrium is. And so it is represented by the ratio of the products over the reactants, the concentrations for both. But with this type of equation here, don't forget there are also powers there. So it can be also represented as this. So the products first, the concentration of the products, okay, so capital C, and raised to the power of the coefficient. So those powers for each chemical is indicated by the coefficient. And multiply, we're not adding, okay, we are multiplying them. And to the power of the coefficient for that one, that would be the little d, over the ratio, over the concentrations of the reactants. We have chemical A raised to the power of its coefficient, the little a right there, and times that to chemical B raised to the power of whatever coefficient that is. And obviously, if these coefficients are 1, you won't be seeing those numbers, and you won't be putting those numbers there. It is just assumed that if there is no number, it is a 1. Okay. So let's go back to this. So from the chemical equilibrium equation, which parts tell us the power that each chemical is raised to? So simply, it's the coefficients. Okay. Now with this equation here, it doesn't really tell you what phases these chemicals are in, if they are let me put this in a different color. If these are in liquids, pure liquids, didn't mean to put a G there, liquids, pure liquids. We don't know if they are in liquids, parentheses L. We don't know if these are in solids, pure solids, or if they're not pure, they are in solution, aqueous. And remember, aqueous, did I spell that right? Okay. Okay, that's better. That looks right. Aqueous. Remember what aqueous means. It is a solution with solutes and solvents mixed together in the universal solvent water. So this is not pure compared to when you see H2O and there's a lowercase l. That means it is pure water and it doesn't have any solutes in there. And also the other one, gas. Okay, so we don't put the ones that are pure liquids or pure solid in this equation here. We only take into account the ones that are in aqueous, a solution, or in gas. And you can also see gases as being in solution when they are out in the atmosphere. We've got the little gas particles mixed in with the bigger parts of the atmosphere, the solvent. So this would only be with the solutions, aqueous or gas. We don't take into account the liquids and the solids because they don't really affect the amount of reactants or products. So rather they are seen as constants, as ones. And usually ones we ignore in math. We don't have to put down the one in this equation here. Okay, so we just don't take those into account. Okay, and going back, dismiss. And going back to this, indicate the phases that are included in the equilibrium constant equation. And like I said, no pure liquids, no pure solids, so just these two. The ones that we can actually measure concentrations. Okay, so now let's take a look at this equation over here. What does the Kc look like for each one? And you guys got to remember what Kc is. Remember that we've got the products at the top to the reactants, and that one goes at the bottom. And also don't forget the powers. Those would be the coefficients. Okay, let me just put that down right there, coefficients. So the Kc for this one, we will do the products first. And these are aqueous, we can put those in. We've got HF, and there's no coefficient there. That means that it's 1. And again, please don't put the 1 there. It's redundant unless you have to put a 1. But, you know, we try not to be redundant. And then the next one, multiply that with the other product, NaOH. We can use that one because it's aqueous. And also there's no coefficient there, so we don't have to put anything at the top there. We know that that means 1. Over the reactants. Look at this one, water. It's a universal solvent, but there's nothing mixed in it. It is pure liquid, so we don't have to put this in there. It counts as 1. But this one is aqueous, so we can use that one. So at the bottom, sodium fluoride. And there's no coefficient, so again, that means that there's a 1 up there. All right? Now for the next one, I want you to do that yourself, okay? Try it out yourself. I believe in you. Okay, so with this one, you are still gonna need your calculator. So this time we are gonna calculate Kc. And we have this equation. Calculate the value of Kc, which is chemical equilibrium, for the reaction to NO2, nitrous oxide, gas. That looks like it can be put into the equation. And it's an equilibrium. Remember, that double arrow tells you it's an equilibrium. And what did I say about equilibrium? The same speed going into the forward reaction and the backwards reaction, turning into products and turning into reactants, the same speed, the same rates at what they are turning into. Okay, so calculate the chemical equilibrium for this chemical reaction if the concentration for NO2 is 0.150 molar and N2O4 is 0.127 molarity. Okay, dinitrogen tetraoxide. All right, so let's do the chemical equilibrium equation. Remember the products at the top. So, and this is in gas, so we can use that one. This one will be N2O4, okay, over the reactants, this one. And that one is NO2. No, you don't put 2 NO2. This is a coefficient, therefore this goes to the top there as the power raised to the second. Right. So that is your equation. We're not done yet. Let's plug in these values. And do our calculation. So for dinitrogen tetraoxide, N2O4, it will be 0.127 molarity divided by, I don't like that line, divided by NO2, which is this, 0.150 squared, okay? And then you can do your calculations. Again, please, if you don't have a calculator, you are not excused from doing this. Use the scientific calculator in Google Classroom. All right, so it will be 0.27, 0.127, yeah, 127, divided by 0.150 squared. Let me see, do we have, oh, we can use this. 0.150, and let's square that. There you go. And that is your answer, 5.6444. I dropped my stylus. So that is your answer. And let's take a looky here. 3 sig figs, 3 sig figs. Let's do this in 3 sig figs. 5.64. So it is 5.64, considered a really large equilibrium constant. So you can assume that this is more towards the forward reaction, as in there's going to be a lot more products being formed than there are reactants. Okay, so for the next one, I want you guys to try this on your own. If you still need help, make sure you come to my live session the next day. Okay, so y'all have a good one. Take care. I'll see you soon. Bye.